Welcome to today's paper reading. Today's paper is titled, LongICLBench, Long Context LLMs Struggle with Long in-Context Learning. This paper introduces LongICLBench, a benchmark for evaluating long context LLMs, authored by Tianle and colleagues from the University of Waterloo, Carnegie Mellon University, and Vector Institute. The abstract discusses the performance of large language models, LLMs, on long sequences, particularly in the context of extreme label classification. A new benchmark, LongICLBench, has been introduced to evaluate these models using 6 datasets with varying numbers of classes and input lengths. The evaluation of 15 long context LLMs reveals that while they perform well on simpler tasks, they struggle with more complex tasks, indicating a need for better long context understanding and reasoning. The study highlights a bias towards labels presented later in the sequence, and suggests that LongICLBench could be a valuable tool for more realistic evaluations of future long context LLMs. Figure 1 illustrates the performance of large language models, LLMs, on a long in-context benchmark across various input lengths. The datasets used have different difficulty levels. As the difficulty of the dataset increases, LLMs face challenges in understanding the task definition and experience significant performance degradation. This highlights the need for improved long-context reasoning capabilities in LLMs. Large language models have advanced into the long-context era, with models supporting context windows ranging from 32,000 to 2 million tokens. These models are applied in various complex tasks such as long-document question answering and multi-document summarization. Key methods include alibi and rope embeddings, which enable training on short sequences and application to longer sequences. Evaluation of these models typically involves language model perplexity, passkey retrieval, and long document question answering. However, these metrics may not fully capture the model's ability to handle realistic long sequence tasks. In this paper, the authors propose using in-context learning on extreme label classification tasks to evaluate long context LLMs, introducing the LongICLBench to assess model performance across different difficulty levels. Figure 2 compares the extreme label in-context learning, ICL, with existing evaluation tasks. Passkey retrieval is highlighted as a synthetic task. Long document question answering is noted for not requiring the entire document to be read to find the answer. In contrast, extreme label ICL necessitates scanning through the entire demonstration to comprehend the full label space for accurate prediction. Figure 3 illustrates the performance of various models across different evaluation datasets, showing a significant decline in performance as the tasks become more challenging. Notably, non-transformer-based models, such as RWKV and Mamba, perform notably worse compared to transformer-based models. However, within a certain range, most models benefit from extensive demonstrations, although this advantage diminishes or fluctuates as the input length increases. In-context learning, ICL, has been shown to improve with an increased number of example demonstrations, but longer input prompts can actually reduce performance. This is partly due to the constraints of the maximum sequence length during training. To address this, memory augmentation and extrapolation techniques have been introduced. Long context techniques for large language models, LLMs, face challenges due to the quadratic increase in computational cost with sequence length. Strategies such as continued fine-tuning and position extrapolation have been explored to manage this. Additionally, alternative architectures have been proposed to handle long inputs more efficiently. Evaluation of long context capabilities is supported by benchmarks like Long Range Arena, LongBench, and Infinity Bench, which include tasks with varying sequence lengths. Table 1 provides an overview of the sub-datasets included in LongICLBench, detailing the number of classes, tokens per shot, and total tokens for each dataset. The datasets cover various task types such as emotion classification, intent classification, and relation extraction, among others. The total token range for each dataset varies, reflecting the diversity in context lengths and the complexity of the tasks. In this section, we discuss the collection of 6 datasets designed to evaluate long in-context learning across different domains and difficulty levels. These datasets range from short to long context lengths, ensuring a balanced sequence token length within each dataset. We also highlight the evaluation of long context language models, including popular open source models and state-of-the-art models like Gemini 1.5 Pro, Claude 3 Opus, and GPT-4 Turbo. These models employ various strategies to handle long contexts effectively. Additionally, we describe the experimental setup, which includes constructing a prompt template for each dataset and ensuring a fair evaluation by sampling the same example set for all models with evenly distributed labels. This setup involves sampling 500 examples from the test set of each dataset to maintain an even distribution in terms of label types. Table 2 provides an overview of the models evaluated in the study, focusing on their strategies for handling long contexts. The table highlights the base models used before any instruction tuning, except for API-based models. It also details the strategies employed by these models, such as ROPE plus LF, position interpolation, and dynamic NTK, to manage longer contexts. Additionally, the table shows the support for different context window sizes, indicating the capabilities of each model and processing extended inputs. In this exploratory experiment, the authors investigate the impact of instance position distribution on model performance in long in-context learning tasks. They explore two main distribution strategies, scattered and grouped. In the scattered distribution, instances are randomly distributed, resulting in a total of 123 distinct instances. This setup shows that models like InternalM 2-7B base achieve approximately 60% accuracy on specific labels, while others like ChatGLM 3-6B 32K perform robustly across a wide range of labels. Conversely, in the group distribution, instances of the same class are positioned adjacent to each other. This reorganization leads to a general decline in performance across most models, with notable drops for models like Mistral and InternalM2. The GPT-4 Turbo model experiences a 20.3% drop in accuracy, highlighting the challenges posed by group distributions. This experiment underscores the varied sensitivity of models to instance positioning, with some models proving more resilient than others. Table 3 presents the results of the Banking 77 dataset with respect to increasing context length. The context length ranges from 2K to 14K, representing 1 to 5 rounds of traversing all instances with unique labels. The accuracy of different models varies significantly across these context lengths. Notably, GPT-4 Turbo and GPT-4o consistently benefit from increased context, maintaining high accuracy even at the highest context lengths. Other models show varying degrees of performance, with some failing to leverage extended context effectively. Table 4 presents the results of various models on the TAC-RED dataset as the context length increases. The models evaluated include Gemma 7B base, Llama 2-7B 32K, ChatGLM 3-6B 32K, Qwen 1.5-7B base, Mistral 7BV 0.2 base, Llama 2-7B LongLoRa, E6B 200K, InternalM 2-7B base, Long Llama Code 7B, RWKV5 World, Mamba 2.8B, GPT-4 Turbo, GPT-4o, Claude 3 Opus, and Gemini 1.5 Pro. The context lengths tested range from 4K to 18K tokens. Accuracy metrics vary significantly, with values ranging from 0.4% to 84.2% across different rounds and models. This table highlights the performance differences among models as the context length increases, indicating which models benefit most from extended context. Table 5 presents the results of various models on the Dialog-RE dataset as the context length increases. The models evaluated include Gemma 7B base, Llama 2-7B 32K, ChatGLM 3-6B 32K, Qwen 1.5-7B base, Mistral 7BV 0.2 base, Llama 2-7B LongLoRa, E6B 200K, InternalM 2-7B base, Long Llama Code 7B, RWKV5 World, Mamba 2.8B, GPT-4 Turbo, GPT-4o, Claude 3 Opus, and Gemini 1.5 Pro. The context lengths tested range from 8K to 32K tokens. Notably, GPT-4 Turbo and GPT-4o consistently demonstrate higher performance across the different context lengths compared to the other models, indicating their superior capability in handling long context dialogue relationship extraction tasks. Table 6 presents the results of various models on the Discovery dataset, which has an extensive label space of 174 classes. The table shows that most models, except for GPT-4 Turbo and Gemini 1.5 Pro, struggle to differentiate among the fine-grained types, often resulting in a score of 0. This indicates a significant challenge in understanding and classifying such a large number of classes. The context length, ranging from 10K to 50K, also plays a crucial role in model performance, with longer contexts generally leading to better results for the more capable models. Figure 4 illustrates the accuracy of each label class when instances are either scattered or grouped within the demonstration prompt. The visualization highlights that models like InternLM 2-7B base show significant sensitivity to the distribution of instances, performing well only when labels are positioned at the end of the prompt. In contrast, models such as ChatGLM 3-6B32K exhibit more resilience to changes in instance positioning. Notably, even high-performing models like GPT-4 Turbo experience a notable decline in accuracy when instances are grouped, underscoring the impact of instance distribution on model performance. In this study, the authors explore the capabilities of large language models, LLMs, in handling long in-context learning tasks, particularly in extreme label classification scenarios. They have curated a dataset called LongICLBench, which consists of long in-context learning tasks with varying difficulty levels based on context length. The research reveals that LLMs experience significant performance degradation when faced with more challenging tasks. Additionally, the exploratory experiments conducted by the authors highlight the influence of the distribution of examples within prompts on the model's performance. The authors hope that LongICLBench and their findings will contribute to ongoing efforts to improve LLM's understanding of long contexts. Thank you for watching.